Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So right now what we're going to talk about is section 2.5, in which we are going to open up the hood on Euler's method and see if we can't improve it a little bit. So this is section 2.5, a closer look at Euler's method. Alright, so what's the matter with Euler's method? We all know that Euler was a genius. And in fact, the more you learn about math, the more you will learn that Euler was, in fact, one of the great geniuses of all of human history. His accumulated works total some ridiculous thing like 800 volumes. And he touched and, in fact, started almost every branch of modern-day mathematics. But his method does lead to a certain kind of error, and let's look at it. So classical Euler's method. So let's just imagine that what we have here is something like this. Let's say this is the exact solution that we should have been getting. Oops. Now, if we were to follow Euler's method here, and let's say that this is x naught, y naught, so initial conditions right there, and we were to draw this out for a little ways, and that's going to be the h, and that's going to give you the x1, y1, and then we were to take it from here, and even if the slope had been correct from here, it would have led us down to there, and then from here, whatever the slope would have been, would have gone out a little bit there. And because of the fact that we're falling further and further behind, our slopes are also not going to be rising aggressively enough to catch up with it, and so we're only going to get more and more behind. And if the slope is changing rapidly, the approximate solution will fall further and further behind. So this is accumulating error. Now here is a suggested remedy, or an improvement. And this is a method that was developed by Carl Hoynes, so it's sometimes called Hoynes' method. Or Hoynes' improved Euler method. So here's the suggested improvement. Rather than taking as gospel the new y value, and then basing everything from there, what we'll do is we'll take what would be the projected new y value, we'll synthesize that with the original one, and we'll blend the two things together to get an averaged slope between the two places. So suggested improvement here is to start by getting the slope from classic Euler. Then find out what the slope would be predicted to be at the next y value average these as a better approximation of the slope. Okay, so rather than taking wherever you land here and using that as the next y value, what we're going to do is the following. So here's the picture. So graphically, let's say we had something and it was going like this, and we were right here to start with, and we wanted, let's say that was h, and that was 2h. So what we would do is we would start off by first projecting our way out here. And that's going to give us our first preliminary y value. And that is like the first draft of the new y value. But then from here, we're going to get our own projection of what the slope should be. So this is giving us like the first draft of the slope. First draft of slope. And then here, we're going to get another thing to consider as the slope. So here, this is going to be the second draft of the slope. And then we're going to average those two things together, which amounts basically to finding the slope directly from here to here. So this is averaged slope. And we're going to cut it off at this point, and this gives us our new y value. So notice that at least in our very rough sketch here, the first version of the path from y0 to y1 takes you pretty far off from the curve. However, by taking the average of this and then cutting that halfway, you end up with actually a much better approximation for where the next y value is going to be. So here's how to actually implement this. So the implementation. Alright, so here are the pieces that we are going to need for the setup. We need an h, which is the step size. We need dy dx is equal to f of xy. So a first order ordinary differential equation, and we need an initial condition y of x naught equals y naught. Okay, so here are the pieces that we're going to be making here. So then k1 is going to equal f of xi yi. So this is like the first draft. Of slope. And then we're going to have a u of I plus 1, which is going to equal y sub I plus h times f x sub I y sub I. So this is like the first draft of the new y value. And then you use this first draft of the y value to get your second draft of the slope, which we'll call k2. So that's going to equal f x sub I plus 1 comma u sub I plus 1. So this is now the second draft of the slope. So it's the second draft of the slope. And once you've got the K2, then we can find the new estimate for the slope by taking the averages of those two things, of the K1 and the K2. So then mi is going to be the average, so 1/2 K1 plus K2. So this is the new estimate for slope. And then the new y value can be arrived at by using that as the value for the slope. So yi plus 1 will be the previous y value plus h times mi. So this is the final draft of the new y value. Alright, so let's try this as an example. We'll just take the example that we were already doing. Take the dy dx is equal to x plus y. We'll take as an initial condition y of 0 equals 1, and we'll take as a step size 0.1. Alright, now the table that we're going to be making here of values is a little bit more complicated than the table that we had for just regular Euler's method, because Euler's method is a very bare bones, very clean, easily implemented method. This one, in order to get a little bit more accuracy, sacrifices some of the simplicity. So we have I of 0, 1, 2, that'll be about enough, or we'll go to 3, but as you'll see, only for the x. Alright, and then we'll have xi, and now here we start with the initial x value, and then we could just go up by the step size. So this one is not different from regular Euler's method, but here's where things start to change. So we have the yi next, which we can only fill in right now for the initial condition. And so the y initial is equal to 1 by assumption. And it is not, we do not have right now the means to get the next y value. We're going to need to find all these other things, the k1, the u, the ui plus 1, the k2, the m, and then finally we can get the y. So now the k1, this is our first estimate of the slope. So this is equal to just the f of xi, yi. So here that's this with these. So it's just going to be 0 plus 1, which equals just 1. And now what happens is we look towards what the future would hold if we were to go at that slope. What would the new y value be? So this is like the proposed y value. So this is yi plus h times k1. So this is what the y value would have been from here using Euler's method. And so that's going to be 1 plus 0.1. So that's where that one takes us. And now we figure out what the slope would have been looking forward to the next x value and if this had been the y value. So that's going to now be the slope is based on this and that. So it's the next x value and this generation's u, or from this row anyway. So it's going to be 1.2. And then finally now we can get the new m. So this is going to be our final draft of the slope, and it's based on the preliminaries of that one and that one. We take the average, which is going to be 1 plus 1.2 is 2.2 divided by 2 is 1.1. So this is 1/2 k1 plus k2. And then finally here, we're able to get the new y using this formula right here. So this is going to be the previous y value, which is 1, plus 0.1 times this, which is going to be equal to 1 plus 0.1, and here it's not too hard, but I don't want to mess anything up, and so I'm going to have, so I just want to be nice and careful, 1 plus 0.1 times 1.1. It's going to be our final little draft of the new y value, and it's 1.11. Alright, well now you just take this and you proceed, so it's going to be 1.21, so this is like regular Euler's method slope, and then this is like the next y value according to regular Euler's method. And so that means what we're going to do is we're going to take that previous y value and then plus 0.1 times that. So it's going to give us now 1.231. And now we're going to take that and use that to get the second draft of the slope. So what we had was the original Euler's method addition of the slope, and now looking to the future, what Euler's method would have said for the next slope. So that's going to be 0.2 to the next x value plus what the next y value would have been, and then that divided by 2. Oh, sorry, not that divided by 2, just that 1.431, and then we take the two k's and we add them together and divide by 2. So that was first k, that was k2 plus 1.21, and then divide by 2. And that gives us our final estimate for what slope we will use from one step to the next. And then we can finally get our new y value by doing 1.11 times, plus 0.1 times that. And that gives us our new y value, 1.2421 if I round it to 4 decimal places. And that's how we would proceed. So my eyes might have been a little bit bigger than my stomach on setting up all these rows. I think one row was enough, or I think this was quite enough to see how this is going to go, and it is quite a hassle to do numerically on paper. Now, your TI-89 is perfectly capable of doing regular Euler's method with the built-in table feature. However, if you wanted to do something like this, you would need to get a lot more creative in organizing your tables, and it would be more trouble than it's really worth. So the TI-89 can't really do Hoyne's method. It can do Euler's method, and it can do Runge-Kuta's method, which is a more sophisticated one, but it can't do the intermediate method, the one that we're dealing with right now. So instead, what we're going to do is we're going to take a look now at what the wider world of technology has to offer on the same matter. Now, when it comes to doing these same sorts of things, but with technology, the best source online that I think for doing this sort of thing is the same one that I've advocated before. So you go to Slope Field Generator, you find the one by Bluffton. So Bluffton University. It's a nice little JavaScript that is designed to do a lot of these things. Now here you have the same differential equation already in it, dy dx equals x plus y, and here we can now customize this a little bit, make x go from 0 to 4 is fine, y go from 0 to 50. Now, one thing about this is it does make a difference. You do want to make sure that your window for the y's includes the values that you're looking for, because the tables that it makes is largely dependent on the window that you've given it for the y values. Now, if you look at the methods that it allows you to choose from for generating your approximate solutions, what we have is classic Euler, and then improved Euler, or the Hoyne method, and then also some other fancier ones. But let's go with the improved Euler Hoyne method. That's a good H, that's a good initial condition, and so we will now submit. And that is a graphical display of what the solution curve that this would generate looks like. Now we can also look at the solution numerically. And here, if you look at the values that have been generated, we have the y's, and they are exactly what we had as well. And also over here, what we had over here were also the slopes, although they've been scaled already by the h. Now, one thing that you can do when you click on this little show details thing is it can also give you the what you could call the the K1 and the K2 here. So the K1 is what they call y1 prime, so it's the first draft of the slope. And then K2 is what they call y2 prime, which is the second draft of the slope. And then the average of those will give you the actual slope that is going to be used. So you can then scroll down this and get more values. The downside on this system is that it doesn't really let you jump over some of the intermediate values quite as easily as some other methods, but it is a good one. Another thing that you can do is, just as we did before with regular Euler's method, we can do this in Excel. Now, to do this in Excel, we have to be a little bit careful in how we set it all up, but we can do it in pretty much the same fashion as we did before, which was just name the things what they are, and essentially just use the same calculations that we did by hand, but just do them in a more efficient spreadsheet fashion. So I'm going to call the various columns here the same things as what were the columns in our previous handwritten version. And K2 and MI. And now, if we start with 0 and 1, and then let it build them up from there, and the x values, we can just make those start from 0 and go up by 0.1, and let it build them up from there. And then for the y's, we have to give it the initial value, but then after that we will build them up by formula, and we'll say equals previous y value plus 0.1, which is the h, times the slope from the previous value. Okay, so now let's go ahead and put that all in, although it doesn't have the pieces yet, of course. Now for the K1s, these are the slopes as would be generated by regular Euler's method. So here, this is just equal to the x plus the y, so that's just going to be equal to this plus that. And then this is what regular Euler's method would have given you as the next y value. So this is equal to previous y value plus 0.1 times K1. And then this is what then the regular Euler's method would have said would have been the next slope, which is going to be our second draft of the slope. So this is going to equal, and it's going to be whatever the next x value is going to be, which is that, plus the previous, or plus the what the next y value would have been, which is there. And then, and I guess actually, I can keep these all going down. Don't put any stock in any of these until all the columns have been filled in. Until then, they're all very tentative, but we can at least let them all do their thing. And then, lastly, finally, we can put in the slopes, which are going to equal the average, so 0.5 times the K1 plus the K2. All right, and now we just go down. And what we now have right here are our new y values generated by the improved Euler's method, or the Hoyne method. And for comparison's sake, let's look at what the exact solution had. So again, this particular differential equation is linear, and it is one that we could have done by just doing the integrating factor. So we can actually figure out, through standard operations, that this is going to be 2 times e to the x, times e to the x minus x, and then minus 1, I believe it was. Sorry. Let's put it down. Yeah, minus 1. So this last part is purely a matter of the initial condition, in fact, but so there's the exact solution, and this we should be comparing against the C column there, which is the estimates. So before, our estimates were okay, but not great. Now, as we start to move along, we can see that the new estimates are in fact quite close to the old estimates, and the errors, although they are still continuing to accumulate a little bit here, are much, much more manageable than they were before. They were getting quite out of hand by even a few entries in before. But now, with the same step size and not relying on any more data than it was using before, with a little bit more sophisticated analysis of that data, we're able to stay much closer to the original values. And you'll notice that the accumulation is a lot less severe as well for these errors. Now, if you wanted on these, you could also view the data making a graph, but that's not really so necessary for us right now. Okay. Well, that is going to be it for us right now. Thank you for joining me for this episode of Math 256. I'll see you again on Wednesday.